So we're now going to finish this chapter with a very neat and very reassuring theorem. And this theorem, theorem 4.22, tells us how we compute the integral of a continuous function of the Brownian. Now, if you just go back to the definitions we've had so far, what would you need to do in order to compute such an integral? Well, f is a continuous function of the Brown, so f of bs is a continuous function of the Brownian motion, so it is an L2 log process. So first you would need to pick up a localizing sequence of stopping time and then say, okay, this is the limit of the Ito integral of H2 processes obtained by localizing f of bs using this sequence of stopping time, this localizing sequence of stopping time. And then you would need to approximate this integral of an H2 process by integral of H2 not process. So you have to exhibit a approximating sequence in H2 naught, and then you would say take the limit of this approximating sequence and then the limit over the family of localizing stopping times, and that is your integral. What theorem 4.22 is telling us is that there is a much simpler expression, explicit expression that converges in probability. Okay, fair enough. So the convergence is only in a very weak topology, but still there is a neat way, at least in probability, to approximate this object, right? Which is limits of various approximations anyway. And this is the way. This is really like in Riemann integration, where you take a left rectangle approximation, right? So your dBs is approximated by a discrete increment of the Brownian on a interval of size, let's take capital T equal 1, of size 1 upon n. And then you just evaluate f of bs at the left-hand side of the interval ti minus 1 to ti. And that's it. So this means that our Ito integral of L2 log process, this extremely complicated objects that we've created through various approximation procedure, really for continuous functions of the Brownian behaves exactly like a Riemann integral, at least if you're being careful enough to do your approximation using the left, evaluating at the left end point of your integral, not the right end point or nowhere in the middle, because if you were to take any other point, you will miss the adaptability of your H2 naught approximation. And that's it. So let's prove this theorem now. So we have to show that the limit of this neat object is the same as the limits of integrals obtained through an appropriate choice of localizing sequence and an appropriate choice of H2 naught approximation of the H2 approximation of the L2 log. So let's do that now. Once we will have the theorem at our disposal, for all practical purposes, we will be able to forget the subtlety of the H2 to L2 log extension, for instance, and just use this limit as a definition of our integral of a continuous function of the Brownian, which is what we will do from that point onwards. Right, so let's see the proof of 4.22. Okay, so the first step is to find an appropriate localizing sequence. We're not going to use the tau and f that we first used to define the Ito integral of an L2 log process. We're going to use a different approximating sequence and then exploit the fact that the definition is independent of the choice of localizing sequence. So the localizing sequence I want to define is like this. It's tau m being the infimum of those t, such that the Brownian gets above m, or you've reached the end of the time interval. Right, that's for all m in capital N. So I'm defining this, and I want to show that this family of stopping time does define a localizing sequence. So first of all, is it clear that this is a family of stopping time? Yes, because bt being greater than m, right? It's a condition involving bt. It's the inverse image by bt of the interval minus mm, which is a closed interval. Bt is ft measurable by definition of ft. Therefore, the set where tau m is smaller than, say, s is in fs, right? because it's a property that you test on the behavior of the Brownian for every values up to that point. So okay, so tau m is a stopping time for the Brownian filtration. Now, is it a localizing sequence? Well, one thing for sure is that the probability of the union of the m of the set where tau m is 1 is going to have probability 1. So why is that? Because the Brownian is finite almost surely, right? Since bt is bounded almost surely. So let's put it this way. Since there exists a set A in sigma, which is probability 0, such that for every omega not in A, t goes to bt of omega is continuous and therefore bounded on 0, 1, because 0, 1 is a compact interval. The image of a compact interval by a continuous function is bounded. So, you know, for every omega outside of the set of trajectories that may be discontinuous, but that set has probability 0, you find that there exists a capital M such that bt of omega is smaller than capital M for all t. Therefore, tau m has to be 1. All right, the other condition has to be satisfied if this one is never satisfied. All right, so that's looking good. The last thing we need to check is that f restricted to the set where s is below tau m. Right, so we need to show that this process is in H2. And the way we're going to show that it's in H2 is we're going to show, let's give a name to that process. Let's say GM. So what we have is that we have that GM is equal to Fm, so at a point omega s, is equal to if Fm of Bs of omega for all omega in omega and for all s in 0, 1, where Fm of x is just the function equal to f of x whenever x is smaller than m. So with the indicator function of the interval minus m. Right? Because what do we do if we stop at the stopping time? We replace this process. Sorry, my f is actually, what is it? It's little f of bs of omega. We replace this by 0 whenever bs of omega is greater than m. So it's exactly the same thing as taking the function f already restricted to those x's that are between minus m and m and plugging in the Brownian. Now that does give me that gm is in H2, because if I look at the expectation of the integral of gm of s squared ds from 0 to 1, this is certainly smaller than the supremum of fm of x in r squared, but fm of x is 0 when x is not in minus mm, so this is the supremum for x in minus mm of fm of x squared, but of f of x, fm and f are equal on that interval, and f is a continuous function. So if I take the supremum of a continuous function on a compact interval, I get something finite. So gm is therefore for every capital M in H2, and that is to say that tau m as a family of stopping time indexed by m is a localizing sequence. Is a localizing sequence for the process s goes to f of bs. Great. So this means, by definition of the L2 lock, of the integral of an L2 log process, and the fact that it's independent of the choice of localizing sequence, that this integral that we're trying to compute, the integral of f of s dbs, is going to be nothing but the limit of the integral of the fm of s dbs as capital M goes to infinity. And now this is a reasonably nice H2 approximation, right? It's an H2 approximation by a bounded function. And this doesn't make sense. I mean, fm of bs and here bs also. Right, so I need to compute those integrals. And how do I do that? There's now an integral of an H2 process, right? I've gone back down from L2 log process to H2 process. And I want to go one step further down back to the original definition of the E2 integral for an H2 not process. So I need to have a good approximating sequence for f capital M. So I'm going to define for all m in capital N and for all n in n, let's call it phi and m to match what's in the note, and that is the sum j equal 1 to n of fm of b j minus 1 over n times the indicator function of the time interval j minus 1 over n to j over n. Right, and that's going to be a function of s in this way. Obviously, it's a process. So this is in H2 naught for every m and every n, because it's of the right form and because this here is certainly fj minus 1 over n measurable, because it's the composition of a continuous function and a process which is j minus 1 over n measurable, right? That's the way fj minus 1 over n was defined, right? It does make the Brownian up to that point in time measurable. So I have an H2 naught sequence, and what I need to show is that this is indeed a approximation of my fm. So I need to show that the L2 norm of that goes to 0 as n goes to infinity for every capital M. All right, so let's do that. Let's write it explicitly and show this convergence of the approximation. So what is the expectation of the integral from 0 to 1 of phi n m of s minus fm of bs? So when I write fm here, that's not what I mean. Fm of bs. So I should say the L2 norm of s omega goes to phi n ms, right? bs of omega. And I take the L2 norm of that process, L2 over omega n 0, 1, and then I show that this goes to 0. So this is what we need to compute. Now, what is that? We can write it explicitly. This is the expectation of the integral. So I've squared the L2 norm, as I always do. And then I've got a sum j equal to 1 to n. And then I've got fm of bj minus 1 over n of s minus fm of b of s, and then this is over the set where s is between j minus 1 over n and j over n. Right. Now again, we use the orthogonality of this indicator function, and we can get the sum out of those integrals by orthogonality, and we get the expectation of the integral from 0 to 1 of fm bj minus 1 over n of s minus fm of bs squared, and we know integrating from j minus 1 over n to j over n ds. Okay, so now I want to exploit continuity properties of the fm. So I'm going to rewrite this as the sum j equal 1 over to n of the expectation. So it's going to be smaller than the supremum of the fm bj minus 1 over n. There's no S here, minus Fm of Bs prime, maybe let's call that Bt rather than Bs prime, squared ds. So I make this independent of S, where t is such that t minus j minus 1 upon n is smaller than 1 upon n. Right. Now I could even forget the j minus 1 upon n and actually let's keep it like that. And now I'm integrating the s, and there's no s anymore in what I'm integrating because I've controlled it by a supremum of all those s's that are in the appropriate interval. And now this gives me 1 upon n times the sum j equal 1 to m of the expectation of this supremum. This supremum where t minus j minus 1 upon n is smaller than 1 upon n of fm bj minus 1 of n minus fm of bt squared. Right. And now, see, I'm summing up n terms, but then I'm dividing by n. So I can control all of that by the maximum values of all j running between 1 and n of this expectation of this supremum. Okay, now I want to start giving some names to that. Let's define maybe mu h is the supremum of fm of x minus fm of y whenever x minus y is smaller than h. Right, so let's define that. And so by continuity of fm, and fm is uniformly continuous because it's a continuous function that is 0 outside of the compact set minus mm. So by uniform continuity, we have that mu of h goes to 0 as h goes to 0. So that's by uniform continuity of fm. Very good. Now that's when x is close to y, but I'm not applying fm to j minus 1 upon n and t. I'm applying it to bj minus 1 upon n and bt. So I now want to also define, let's call that mjn, and mjn is going to be the supremum for all t's that are close enough to j minus 1 upon n, right, of bj minus 1 upon n and bt. Now, I'm claiming that this also goes to 0 as n goes to infinity, almost surely. And that is because the trajectory of the Brownians are continuous, and 0, 1 is a compact interval. So what we have is t goes to bt is uniformly continuous, almost surely. And not only those suprema do go to 0 almost surely, but even if I take a maximum of those of a j equal 1 to n, so I pick any interval of side lengths 1 upon n, because the continuity is uniform, I get that the maximum j equal 1 to n of the mjn goes to 0 as n goes to infinity, and that happens almost surely. Right, so really the thing that I'm trying to estimate, which is the L2 norm of the difference between the what I hope is an approximating sequence and what I want to approximate, which is fm of bs of omega, the L2 norm of that squared is smaller than the expectation of the maximum j running between 1 and n of my mu's of mjn. right? And I know that the mjn's go to 0 almost surely. And I know that my mu of h goes to 0 as h goes to 0. So what I have is that, oh, that's squared. The maximum j equal 1 to n of mu of mjn goes to 0 as n goes to infinity almost surely. Now, I need convergence in L2, right? I need this expectation of that to go to 0. So in order to do that, I need some uniform integrability or some dominated convergence. But I do have dominated convergence because what is mu of mjn, right? It is certainly always smaller for almost every omega than twice the supremum of fm of x for all x in R, right? Because it's defined at some supremum of fm of bj minus 1 over n minus fm of bt. And that is certainly a fixed number, a fixed finite number, because fm is a continuous function that is 0 outside of a compact set, and the image of the compact set by a continuous function is bounded. So this is a number. Let's call that number k, right? And so what we have is, and k is a number, so it is a L infinity random variable, therefore it's an L2 or L1 random variable, well, 2 if I square it to space. And so by dominated convergence, this is true for almost every omega in omega. So by dominated convergence, I've just proven that phi n m is a approximating sequence for the process s goes to fm of bs. All right, so that is to say what? That is to say that this integral that I'm trying to compute, right, is the almost sure limit. So this is the limit of the integral from 0 to m of fm bs dbs as m goes to infinity, and that is true for almost every omega. And then this integral in turn is the L2 limit. So let's write that in L2. This minus the integral from 0 to 1 of phi n m of s dbs in L2 goes to 0. These are the two things we've proven, and that takes us very close to computing our integral of f of bs dbs, because the integral of phi n m of s dbs, that we know exactly what it is. We know that this is the sum j equal 1 to n of f capital M of bj minus 1 over n times b, what is it, bj over n minus bj minus 1 over n. So this is almost what we want, except we've got f capital M instead of fm. But at the moment our limit is taken in L2 norm, and we're going to downgrade that to a limit in probability. So now, to get the limit in probability, we're going to define an of epsilon for every epsilon and for every n as the set of all those omega, such that this sum that I'm interested in is close enough to the integral I'm trying to compute, which is f of bs dbs. So, right, so we need to show that the probability of an epsilon goes to 0 as n goes to infinity for every epsilon. that would conclude the proof. Okay, how do we do this? Well, let's give ourselves a capital M in n. What can I say about the probability of an epsilon? Well, it's two possibilities. It's either tau m is 1 or tau m is not 1. So this is certainly smaller than the probability of tau m being smaller than 1 plus the probability of an epsilon intersected the set where tau m is equal to 1. Right. Now, okay, so this is smaller than 1 minus the probability of tau m being 1. And as I send m to infinity, this is going to go to 0. And then plus, okay, how do I estimate that? I estimate that in the following way. So this is the probability of the set where sum of j equal smaller than the probability of the set where sum of j equal n fm bj minus 1 of n times bj minus 1 of n minus the integral 0 to 1 of fm of bs dbs is greater than epsilon. Now, why is that? Because if tau m is 1, then f is nothing but fm, because fm is by definition f stopped up at the time tau m. But if tau m is 1, then you never stop. So f and fm are equal on that set. And that's the point why we are decomposing into when tau m is smaller than 1, and therefore f is not equal to fm, and when tau m is equal to 1 and f is equal to fm. So now I can use this, well, I know what that is, but I can use this fact. I can use the L2 convergence of the integral of phi and m to the integral of fm bs to say that this is smaller than 1 minus probability of tau m being 1 plus 1 upon epsilon square times the L2 norm of the integral of fm bs dbs from 0 to 1 minus the L2 norm of the integral of phi n m of s dbs. And that is squared. Okay. And the point is that now, certainly as I send n to infinity, this L2 norm goes to 0, because that's what we just proved here by proving that phi n m is an approximating sequence for the process as goes to fm bs. So this thing here, by taking a limit as n goes to infinity, has to tend to something that is smaller. So let's put it this way, it's going to be neater. The limit of the probability of an epsilon as n goes to infinity is always going to be smaller than 1 minus the probability of tau m being 1, and that is for all m in n. And this is the probability that tau m is smaller than 1. And if this is true for all n, then I could take the infimum of that, and so I would get that this is to be smaller than the probability of the intersection of this set where tau m is 1. Right, and that is the probability of the complement of the unions of the sets where tau m is 1. And that set has probability 1, so its complement has probability 0, since tau m is localizing for the process s goes to f of bs. And that concludes the proof. So that tells us that whenever we have a continuous function of the Brownian, so a spatial kind of L2 log process, we don't have to go through the entire theory of construction of E2 integral of L2 log process, construction of E2 integral of H2 process. This is all now encapsulated in the proof we've just finished, and we can just say what is the E2 integral of the continuous of a continuous function of the Brownian? Well, it is the limit of the Riemann sum as long as you evaluate your continuous function of the Brownian at the left-hand side of the rectangles. Okay, and that concludes this chapter, and we will see that now that we have such a good, very close to Riemann integration way of computing Riemann integrals, then we are in a position of proving a analog of the fundamental integral of fundamental theorem of calculus, and that will be our next chapter, proving Ito formula, which will give us then very concrete way of computing Ito integrals.